Welcome to Study Loop.
Hello everyone, today we're doing chapter 23, problem 54, and this problem asks us for two things. In A, which is the first page, it asks us to determine the identities of intermediates A to C, while in B, it asks us how treatment with LDA and CH3I doesn't form ibuprofen, but another product, and determine that product and why it's formed. So let's start with A, and then we'll move on to B. So in A, we're just trying to form ibuprofen here, and we're starting from this starting material, and then we're adding sodium borohydride in methanol. So what this is, well, you're adding a reducing agent here. So from this aldehyde, you're going to reduce it down to an alcohol. So we can say that from this aldehyde, for A, we're going to reduce that to a primary alcohol. Now, A to B, so product B, well, we're adding PBr3. So what we know is that oxygen will act as a nucleophile to attack this phosphorus nucleus, and then it's going to make alcohol into a much better leaving group. So once it's a much better leaving group, we're going to add sodium cyanide. So sodium cyanide associates to Na plus and Cn minus. So our nucleophile is going to be this carb anion here, and that's going to do an SN2 180 backside attack to kick off the newly formed good leaving group in replace for the cyano group to form product B. So now you're going to have the cyano group being formed. And now form B. Now for C, you're adding LDA and an alkyl halide. So LDA will deprotonate your most acidic proton, and that's going to be your alpha proton to the cyano in this case. So you're going to deprotonate that to make that into a strong nucleophile, in which you're going to add an electrophile here. So you're going to have that extra carbon, the methyl group, being added at this alpha position to form product C. And you have that methyl group, and then through acid hydrolysis, you form ibuprofen. You just change identity of the cyano group to this carboxylic acid. So this is part A. Now in part B, it asks us something else. So in part B, it gives us a structure D, and it says that direct alkylation of D with treatment of one equivalent of LDA and CH3I does not form ibuprofen. Why is that? And explain the product that's formed. So if you react this with LDA and CH3I, well, LD, like mentioned before, will rip off your most acidic proton. So in the previous case, the most acidic proton was the alpha proton here. This would be the most acidic out of this entire molecule. But in this structure D, if I were to just redraw that underneath here, we actually see something interesting, that the most acidic proton in this case now is not the alpha position. It is actually the carboxyl position. So this proton here is a lot more acidic than the proton that comes off this alpha position. Actually, in physiological pH, carboxyl groups exist in its anionic form because the pKa of this proton is so low. So it's going to be deprotonated. So LDA is just going to rip off this proton very easily to make this oxygen now a anoxide, so a negatively charged oxygen. And that is going to act as a nucleophile to do your SN2 attack to form now a new ester. So your carboxylate anion is going to form with a CH3I to form an ester substitution product. And this is why you don't form ibuprofen here, because that alpha proton is now considered the second most acidic proton, not the most acidic in this case, because the carboxyl group here was now protonated instead of deprotonated.